An earthquake is the shaking of the surface of the earth resulting from a sudden release of energy in the earth's lithosphere that creates seismic waves. Earthquakes can range in size from those that are so weak that they cannot be felt to those violent enough to propel objects and people into the air and wreak destruction across entire cities. The seismicity, or seismic activity, of an area is the frequency, type, and size of earthquakes experienced over a period of time. The word tremor is also used for non-earthquake seismic rumbling. At the Earth's surface, earthquakes manifest themselves by shaking and displacing or disrupting the ground. When the epicenter of a large earthquake is located offshore, the seabed may be displaced sufficiently to cause a tsunami. Earthquakes can also trigger landslides and occasionally volcanic activity. In its most general sense, the word earthquake is used to describe any seismic event, whether natural or caused by humans, that generates seismic waves. Earthquakes are caused mostly by rupture of geological faults but also by other events such as volcanic activity, landslides, mine blasts, and nuclear tests. An earthquake's point of initial rupture is called its hypocenter of focus. The epicenter is the point at ground level directly above the hypocenter. Tectonic earthquakes occur anywhere in the earth where there is sufficient stored elastic strain energy to drive fracture propagation along a fault plane. The sides of a fault move past each other smoothly and aseismically only if there are no irregularities or asperities along the fault surface that increase the frictional resistance. Most fault surfaces do have such asperities, which leads to a form of stick-slip behavior. Once the fault has locked, continued relative motion between the plates leads to increasing stress and therefore stored strain energy in the volume around the fault surface. This continues until the stress has risen sufficiently to break through the asperity, suddenly allowing sliding over the locked portion of the fault, releasing the stored energy. This energy is released as a combination of radiated elastic strain seismic waves, frictional heating of the fault surface, and cracking of the rock, thus causing an earthquake. This process of gradual buildup of strain and stress punctuated by occasional sudden earthquake failure is referred to as the elastic rebound theory. It is estimated that only 10% or less of an earthquake's total energy is radiated as seismic energy. Most of the earthquake's energy is used to power the earthquake fracture growth or is converted into heat generated by friction. Therefore, earthquakes lower the Earth's available elastic potential energy and raise its temperature. Though these changes are negligible compared to the conductive and convective flow of heat out from the Earth's deep interior. There are three main types of fault, all of which may cause an interplate earthquake: normal, reverse, and strike slip. Normal and reverse faulting are examples of deep slip, where the displacement along the fault is in the direction of deep and where movement on them involves a vertical component. Normal faults occur mainly in areas where the crust is being extended, such as a divergent boundary. Reverse faults occur in areas where the crust is being shortened, such as at a convergent boundary. Strike-slip faults are steep structures where the two sides of the fault slip horizontally past each other. Transform boundaries are a particular type of strike-slip fault. Many earthquakes are caused by movement on faults that have components of both deep slip and strike slip. This is known as oblique slip. Reverse faults, particularly those along convergent plate boundaries, are associated with the most powerful earthquakes, megathrust earthquakes, including almost all of those of magnitude 8 or more. Megathrust earthquakes are responsible for about 90% of the total seismic moment released worldwide. Strike-slip faults, particularly continental transforms, can produce major earthquakes up to about magnitude 8. Earthquakes associated with normal faults are generally less than magnitude 7. For every unit increase in magnitude, there is a roughly 30-fold increase in the energy released. For instance, an earthquake of magnitude 6.0 releases approximately 32 times more energy than a 5.0 magnitude earthquake, and a 7.0 magnitude earthquake releases 1,000 times more energy than a 5.0 magnitude of earthquake. An 8.6 magnitude earthquake releases the same amount of energy as 10,000 atomic bombs like those used in World War II. This is so because the energy released in an earthquake, and thus its magnitude, is proportional to the area of the fault that ruptures in the stress drop. Therefore, the longer the length and the wider the width of the faulted area, the larger the resulting magnitude. The topmost, brittle part of the Earth's crust, and the cool slabs of the tectonic plates that are